Let's look at OpenStax College Physics, Chapter 18, Problem 47. Find the electric field at the location of Q1 in figure 1853. Given that QB equals QC equals QD is plus 2 nanocoulombs, and Q is negative 1 nanocoulomb, and the square is 20 centimeters on a side. So let's write down the things that we know and then what we're looking for. And I've already color-coded my different charges, and I'm going to try to stick with those colors. So for now, I'm going to write down the things that I know. So I know that QB equals QC equals QD, and that's plus 2 nanocoulombs, and just Q is negative 1 nanocoulomb. We also know that the distance between the charges, the side of the square really, is 20.0 centimeters, and we're looking for the electric field at QA. All right, so we have 5 charges here, QA, B, C, D, and this Q, and we're looking for the electric field at this location. Now, at this location, QA does not contribute with an electric field because it's right at that point. So we only want the electric field due to charges B, C, D, and Q. So we'll have to do superposition. We'll have to look at the electric field due to each of those charges at this point and then add them vectorially. So we'll start with charge QB, and I know that the electric field come out of positive charges, so this would be the electric field of QB, but at the location of A, that means that the electric field will be away from QB, so to the left in the drawing. And I'm going to call this E sub B. Then for charge C, again, the electric field are going to point away from it because it's a positive charge, and that means that at the location of A is going to go in this direction, so I'll call this E sub C. Then charge Q is a negative charge, so that means that the electric field lines go towards charge Q, like this. So at the location of A, the electric field due to charge Q is going to be in this direction, and I'm going to just call this E sub Q. And then the last one is Q sub D. It's a positive charge. The electric field lines radiate outward from a positive charge, and that means that at the location of QA, the electric field will be in this direction, away from QD, and that is E sub D. So I have the electric fields due to these charges. Now, I noticed that they are in several different directions, so I will have to pick a positive x and a positive y-axis, so I'm going to go with positive y straight up, positive x to the right. So this is my plus x, and this is my plus y. The x doesn't look very much like an x. Okay, so that means that I'm going to have to break these two electric fields up into x and y components, but first let's just figure out what the different components of the electric field are for the due to the different charges. So E sub B is going to be K, absolute value of QB, divided by the distance squared. So the distance is from charge B to charge A, and we're told that that's 20 centimeters. So that would be, I just called it D. So we have D squared. So that will be 9 times 10 to the 9th. QB is 2 times 10 to the negative 9th coulombs, divided by 0.2 meters quantity squared. And when we plug our numbers into the calculator, we end up with 450 newtons per coulomb. Then for charge C, electric field sub C is K absolute value QC divided by the distance squared. So again, the distance is from charge C to charge A, and that is the side of the square. So that will be, again, D squared. So that's 9 times 10 to the 9th times 2 times 10 to the negative 9th divided by, again, 0.2 meters squared. So we get 450 newtons per coulomb for this force as well. Now we have to look at charge Q, and the electric field due to charge Q at this point points towards charge Q, and it has a magnitude of K charge Q divided by the distance from here to there squared. So what is the distance from here to there? Well, let me just draw a small square over here. I know that this is distance D, the side is D, which makes then the diagonal, if this is D, that is D, the diagonal is going to be square root of D squared plus D squared, or D root 2. Now, Q is at the center of that, so that means that the distance I'm looking for here is actually D root 2 over 2. So D root 2 over 2 is what we need for charge Q. So let's write that out. We have the electric field due to charge Q is K, absolute value of Q, divided by, what did I say, D root 2 over 2 quantity squared. So that is 9 times 10 to the 9th. Q is, in absolute value, 1 times 10 to the negative 9th, divided by D is 0.2 times square root of 2 over 2 quantity squared. And we end up with 225 newtons per coulomb. So we have one more electric field we have to calculate. That's due to charge QD. So electric field due to charge D is K, absolute value of Q sub D, divided by the distance from QD to QA squared, and that distance is this diagonal that I said earlier was D root 2. So that would be D root 2 quantity squared. So that's 9 times 10 to the 9th times 2 times 10 to the negative 9th divided by 0.2 square root of 2 squared, and that turns out to be 225 newtons per coulomb. So now we calculated all the different electric fields due to the 4 charges. But now we need to find the x and y components of the electric field due to Q and the electric field due to D. So I'm going to draw projections onto the x and y axis for both of these. So I'm going to have an x and a y here, and I will have to calculate what those are. So a projection of ED onto the x-axis gives me E sub D x, and a projection of EQ over the x-axis gives me E sub Q x. And then we do the same thing in the y direction. So I'm going to project ED onto the y-axis and end up with EDX y, and I'll project EQ onto the y-axis and end up with EQY. So now it's kind of a mess. There's a lot of stuff written on there, but I try to stay, I try to color code this. So my x direction are all the pink lines and my y direction are all these light blue lines. So I can then say that the electric field in the x direction will be E qx minus E dx minus E sub b. And since the angle is 45 degrees, then I have EQ minus E d cosine 45. I could have used sine 45 as well, minus E sub b. And when we plug in the numbers, we end up with negative 291 newtons per coulomb. Then in the y direction, we have E sub c going up, so E sub y is EC is positive, plus E dy minus E qy, and that will be, again, we can, again, we'll use trig, so it's going to be E sub c plus E d minus E q times sine 45 degrees. And when we plug in the numbers, we end up with 291 newtons per coulomb. So that means that the electric field is going to be the square root of Ex squared plus Ey squared. So that will be square root 291 squared plus 291 squared. And we end up with 412 newtons per coulomb. And since the x and y components are equal to one another, that means that the angle is going to be 45 degrees. And it will be in which direction? So let's see that quickly here. We know that the x component is that way. We know that the y component is positive. So the x component is negative because we have a negative value for it. The y component is positive because we have it going up. So that means that the electric field is in this direction and the angle is 45 degrees. Either this one is 45 or that one is 45.